Okay, welcome back everyone. This video is going to be on polar form. We're going to first explore what polar form is, then we're going to look at converting from Cartesian form to polar form, and then from polar form back to Cartesian form. Now, before we jump into polar form, I want to first refresh our memories on the unit circle we looked at in Unit 2 during our trig identities topic. So here I have a Cartesian plane, I have a nice x and y axis, and I have this little pink circle here. Now, normally if this is the unit circle, I say, well, it's a unit circle, therefore it has a radius of 1. That's the premise behind the unit circle. It's got a 1 unit radius. However, instead of looking at this with a radius of 1, we're going to look at it with a radius of r. So instead of being strictly a unit circle, this is just any circle centered around the origin, and I have some little orange line out here to the side of my circle. I can say the coordinates of this point on the outside of my circle is equal to whatever my x coordinate is at that point and whatever my y coordinate is at that point. So this is going to be nice and algebraic. It doesn't matter what these two numbers are specifically, it's just going to be whatever my x-coordinate is and whatever my y-coordinate is, because my circle is centered around the origin. If I create a right triangle, if I make a little broken line down here, and I draw a little red line across the base, I can get a length for the base and a length for the height based on my coordinate points over here. If this is simply the x-coordinate, then the length of my red line is going to be equal to whatever my x-coordinate is at that point. For the height of my triangle, with the same logic, well, my height is simply going to be my y-coordinate. And just to kind of highlight this idea, if I look at the length here of this line on my triangle, and I kind of come across to my y-axis, you're going to find that these are going to be the exact same length. So let's say that this coordinate point here was a half, then the length here would be a half. So again, we're keeping this algebraic. The height of my triangle is simply just equal to whatever my y-coordinate is at that specific point. And that height will change depending on where that point is. Okay, if I get rid of the highlighter and those numbers and I go back to our original picture, I can now explore over some angle theta. And if I use SOHCAHTOA, I use our basic trig skills, I can create expressions for x and for y in terms of r. So if I look at theta and I take sine theta, well, sine theta is equal to opposite divided by my hypotenuse, which is going to become y divided by r. Equally, if I look at cos theta, well, cos theta is going to be equal to my adjacent x divided by my hypotenuse r as well. If I write each of these in terms of y and in terms of x, then I'm going to wind up with r sine theta is equal to y, and r cos theta is equal to x. Okay, so I have an expression for y is equal to r sine theta, and I have an expression for x is equal to r cos theta. Well, if we come back to my little orange coordinate points, if this is my x-coordinate, I can see x over here is actually equal to r cos theta, and if my y-coordinate here is equal to r sine theta, then I can rewrite this coordinate point, instead of being x and y, it can be r cos theta, comma r sine theta. Okay. So I now have a new expression for these coordinate points. And where this is really useful is if I convert this from our Cartesian plane to an Argand diagram, if I replace my x and my y with my imaginary axis and my real axis, then my coordinate points, if I'm now in an Argand diagram, instead of being r cos theta, comma r sine theta, I now add those two components. So this is going to become, I might just change the color for this. This is going to become r cos theta plus r sine theta. But now I have an imaginary axis, so I need to include the I on the side here. Now what I've discovered here is actually my polar form for any complex number. What this means is that if I have any complex number, a plus bi, I can represent that as a point on my Argand diagram. So I can represent a plus bi as a point on my Argand diagram. And I can say that's equal to r cos theta plus r sine theta I. It's the same thing. My complex number can be expressed as a plus bi, or it can be expressed as r cos theta plus r sine theta, where my r relates to the length of this line here. So the r in these expressions is the length or the magnitude or the modulus of my complex number. And my angle theta relates to the angle it makes with my Cartesian plane, or with the real axis on my Argand diagram. So I can express complex numbers in two ways: a real component plus some imaginary component, or in polar form as r cos theta plus r sine theta I. Now, this r cos theta plus r sine theta I, we use it so often that this has an abbreviated form. So the way we write this abbreviated form, if I scroll down to give myself a little bit more room, is I can write r cos theta, r sine theta as being r cis theta. I think of this as the c for cos, the s for sine, and the I for imaginary. This is an abbreviated version of the same thing. And just note, there's what we call the principal argument of polar form, where I always express theta in radians between negative pi and positive pi. So essentially, if my complex number is in quadrant 1 or quadrant 2, it's going to be between 0 and positive pi. If it's in quadrant 3 or quadrant 4, I'm going to express that in terms of negative pi. It's also important to note that r is typically referred to as the modulus, and theta is typically referred to as the argument. As a result of that, this is sometimes referred to as modulus argument form, or we could have questions that specify what is the argument of the complex number. If the question asks for the argument, we give the angle the complex number makes with my real axis in my Argand diagram. Okay, let's look at converting from Cartesian form to polar form. So Cartesian form is the standard way we've been writing complex numbers in previous lessons, where I have my real component and I have my imaginary component. Now, to convert between Cartesian form to polar form, remember our polar form looks like r cis theta, where r is the modulus of z and theta is the angle z makes with the Argand diagram, or the real axis of my Argand diagram. So first up, let's find the modulus of z. The modulus of z is going to be equal to the square root of root 3 squared plus minus 1 squared. Well, root 3 squared is just going to become 3, minus 1 squared is going to become positive 1. This is going to give me the square root of 4. So that means the modulus, or the magnitude of z, is going to be equal to 2. So once I've found r, and I could write this instead of being, the modulus of z like this, I could simply just write this as r. Once I've found r, I now want to find my angle. Well, for every single complex number, my angle is going to be equal to tan theta is equal to my imaginary component divided by my real component of my complex number. Again, this is really similar to what we did with our vectors. It's going to be tan theta is equal to my y-axis divided by my x-axis, or tan theta is equal to sine divided by cos. In this case, my y-axis is my imaginary axis, and my x-axis is my real axis. So for complex numbers, tan theta is equal to my imaginary component divided by my real component. So in this question, my imaginary component is minus 1, and my real component is the square root of 3. If you remember our exact value triangles, 1 over root 3 is going to be pi on 6. Because the imaginary component, or my sine component of my solution, is negative, then that means the angle between my complex number and the real axis is going to be pi on 6 in the quadrant where sine's negative and cos is positive, which in this case is going to be quadrant 4. So therefore, theta is simply just going to equal negative pi on 6. To formalize this into polar form, therefore, root 3 minus I is equal to 2 cis negative pi on 6. And again, if I look at my angle, it's between negative pi and pi. Negative pi on 6 is between those boundaries, so I can just leave my angle as is. Just note, if I got something like 7 pi on 6, I would have to then adjust my angle to make it negative 5 pi on 6. And if I quickly consider my angle, negative pi on 6 is between negative pi and positive pi, so I don't need to do anything to simplify my angle for this question. Okay, so converting from polar form to Cartesian form. If I recall, polar form is actually r cos theta plus r sine theta I. So all I need to do is take my r from my polar form and my angle from my polar form and simply just plug those in and then simplify my equation. So if I go ahead and put my r and my theta into r cos theta plus r sine theta I get 4 cos pi on 3 plus 4 sine pi on 3I. Again, using my exact values, pi on 3 is the same thing as 60 degrees, so therefore cos of pi on 3 is going to become a half. So that becomes 4 times a half plus 4 times, well, sine of pi on 3 is root 3 over 2I. If I simplify all of that down, 4 times a half is going to give me 2 plus, well, 4 divided by 2 is 2, so 2 root 3I. Okay, so that's it for this video. We've learned what polar form is, how to convert from Cartesian form to polar form, and how to convert from polar form to Cartesian form.